This chapter 5 teaches you what is meant by a bond's convexity and explains why it is important to take this convexity into account when estimating a bond's price changes for large movements in yields. Returning to our earlier table, which illustrated the application of modified duration, which is reproduced here for convenience, we recall that as we allowed yields to move by significant amounts from the original level of 8%, we found our linear approximation for the bond's price changes to become increasingly inaccurate, suggesting a curvature in the actual shape of the real graph. This curvature in the shape of the graph is known as convexity and becomes increasingly pronounced as we move further and further away from the original yield level. It turns out that convexity, like duration and modified duration, has a formula we can program into Excel, which looks like this. Unfortunately, Excel does not contain a pre-programmed function for convexity, so we have gone ahead and programmed this formula into the next worksheet you're about to see, labeled convexity. The similarity of this worksheet to the one labeled duration should be apparent, which is not really surprising given the similarity between the formula for convexity, reproduced here in the bottom rectangle for your convenience, and that for duration, which by now you have probably memorized. The key differences are the following. First, in addition to multiplying the PV of each cash flow by what we previously called its age, i.e. by T in the formula, we also multiply each of these terms further by T plus 1. Second, when we sum all these terms and obtain the amount shown in the cell G27, we then proceed in G31 to divide the total by the square of the discounting operator 1 plus y over f, hence the cross-reference to D7. And third, we also divide the result that we just reached not simply by f times the price, where f of course is the frequency, but rather by f squared. Geeks once again may have realized that convexity is derived by differentiating the formula for modified duration with respect to y once again, which amounts to saying it is the second derivative of the price function with respect to yield. So now, working your way through this worksheet, and in particular through column G, which, as we said, represents in each cell the PV of each cash flow times its age times its age plus 1, summed together in cell G27, and then divided by the appropriate divisors in cell G31, you should have no difficulty confirming that the convexity of this 8% 10-year bond at a yield to maturity of 8% is 60.17, as indicated in this cell G31. It is not possible to understand such a number intuitively. Unlike duration, where the number derived from the formula can be intuited either in terms of the average time it takes to receive in present value terms the amount of your initial investment, or alternatively as a sort of multiplier that converts yield movements into percentage price changes. It suffices to understand that the greater this number, the more you should expect the correct graph for the bond's price-yield relationship to deviate away from the straight line representing the linear approximation based solely on modified duration. It is not possible to understand such a number intuitively. Unlike duration, where the number derived from the formula can be thought of either in terms of the average time it takes to receive in present value terms an amount equivalent to the initial investment, or, thinking a little more about modified duration, as a sort of multiplier that converts yield movements into percentage price changes. It suffices to understand, however, that the greater the convexity number, the more you should expect the correct graph for the bond's price-yield relationship to deviate away from the straight line representing the linear approximation involving modified duration. So, now that we have a grasp of the equation for convexity, can we use the number to improve our estimates of percentage price changes given a certain yield movement? The answer is yes, as evidenced by this formula, which begins as before, but then adds an additional term in its last row, known as the convexity adjustment, after the plus sign you see towards the middle. Before applying this formula, we point out that whether yields move up or down, the squaring of the yield change in the last part of the formula ensures that the convexity adjustment is always positive, which is a very welcome bond characteristic for a bondholder. While the bondholder will still have losses if rates rise, the greater the bond's convexity, the more the actual loss will be reduced by virtue of the convexity adjustment versus what it would have been under the linear approximation alone. And when rates fall and the bondholder has gains, those gains are magnified further by the convexity adjustment, with the more convex bonds experiencing the greatest magnification. Our final worksheet, labeled Convexity Adjustment, examines the effect of the convexity term in the above formula and verifies that it improves the price change estimate versus our earlier linear approximation. This worksheet is identical to the one labeled Mod Der Illustration, except for the additional column D, which includes in each cell the formula for the convexity adjustment, appearing here right after the plus sign. It quickly becomes apparent from an examination of columns D and F that this time the accuracy of our estimate is almost perfect for what is up to a 100 basis point movement in yields up or down, and continues to be very accurate when the yield movement reaches 200 basis points, again in either direction. It would be possible mathematically to incorporate yet more terms into our equation for the estimation of percentage price changes that would improve its accuracy even further. But this is rarely done in practice, since we have already reached a more than acceptable level of accuracy for most purposes. We inevitably conclude by asking how a bond's convexity may be affected by our three friends from earlier, namely the coupon, the tenor, and the yield to maturity. Since, unfortunately, Excel does not have convexity programmed as a function, we have reverted to this previous worksheet convexity and will now proceed manually to make changes to the inputs as appropriate, asking you, of course, to keep your eyes focused on the output for convexity in cell G31. We note on this worksheet that first a reduction in coupon, for example to 5%, causes convexity to increase, while an increase in the coupon rate, for example to 11%, does the opposite to convexity. We also note, holding now the coupon constant at 8%, that a reduction in the yield to maturity from 8% to, for example, 5% similarly causes convexity to increase just like before, while an increase in the yield to maturity to 11% does the opposite to convexity. With regard to maturity or tenor, we would need, as you can see, to rework the entire worksheet if we wish to model the convexity of bonds with different maturities. So, in the interest of time, we will skip this step, but simply inform you and hope that you will believe us when we say that the longer the tenor, the greater the convexity, and vice versa. You may have noticed that each of these relationships runs exactly parallel to the ones we had established for duration and modified duration. So our earlier table, in which we summarized our results, can now be expanded to look as shown here, with identical entries across each row, of course. This completes this chapter 5 and brings us to the quiz.